Okay, so I hope everybody simplified that. There are some clever tricks that you can pull that maybe not everybody noticed, so I'll show you that. So we have this stuff. So one thing that will really simplify it, if you notice this, you can reduce the 8 and the 6 right away to 3 and 4. More importantly, you can reduce the n cubed and the n, and just make that n squared. That way you don't have to distribute the n over, right? Otherwise you would have to reduce it out at the end. Okay, so now what I'm going to have is 4, and then I'll go ahead and FOIL this stuff out. I get 2n squared plus 3n plus 1. In the denominator, I've got the n squared and the 3, so I'm going to put 3n squared. All right, so that equals 8n squared plus 12n plus 4 over 3n squared. All right, now let's just take a moment to appreciate that. This is the sum from I equals 1 to n of a sub I. It gives a right-hand sum, we sometimes use RHS to abbreviate right-hand sum, for any number of rectangles n rectangles. Now, it only works for the particular function that we're dealing with, 4 f of x equals x squared, and only on the interval that we're dealing with, which is 0 to 2. All right, so I picked a very contrived function because we can do this, but we're going to see later that actually you can do this with any function, and we don't have to do this depth of analysis. But I want to show you that you can take the limit as n approaches infinity of a right-hand sum. So look, this expression gives me the total, the sum of the a sub i's for any number n, right? Let's say I wanted 1,000 rectangles in there. I wanted to estimate that with 1,000 rectangles. Look how easy this is. It's 8,012,004 over 3 million. That's the sum. That's the sum of 1,000 rectangles. Boom, easy. Okay, so that's very powerful, but in itself. But even more powerful is that you can now do the limit as n approaches infinity of this expression, 8n squared plus 12n plus 4 over 3n squared, which is in fact what you were asked to do in number, if I can find the correct page, in part 2, find the limit as n approaches infinity of the expression in number 7. By the way, you have to turn me in your own copy of this, just to show that you are really doing it doing it as we go along. You have to turn in your own copy of, it really can be exactly like this, but I want you to really write it out so that you can go through it step by step and try to understand it step by step. Don't just, be unconscious of it. All right. Yeah, we can do that limit. That's what we're doing in part 2. And, appreciate what you're looking at there. Look how easy this limit is to do. What is the limit? Yeah, it's 8/3, because the degree of the numerator and denominator match. 8/3. You can go back to all those estimates that we did with the upper bound and the lower bound. 8/3 falls in between all of them. All right, so it's a plausible area. I mean, think about what this is really doing, that this is the limit as n approaches infinity of the sum from I equals 1 to n of a sub I. You've done that limit. It's 8/3. So you have done the limit as n approaches infinity of a Riemann sum. And this sum overestimates, so the sum overestimates A because right-hand sum is used on an increasing function. So we talked about that before. A right-hand sum is used on an increasing function. The sum is going to be an overestimate because the little rectangles hang over, right? They hang over the area. So that means that our true area has to be, in a certain sense, what do we know about it? We know that the true area could be less than 8/3. It can't be more than 8/3. The true area cannot be more than 8/3 because the little rectangles hang over. But our suspicion, because we have a limit as n approaches infinity, maybe the area is equal to 8/3. We don't know that it's not. So we know that the area cannot be greater than 8/3. So let's just say for now that the area is less than or equal to 8/3. Maybe it's equal. It seems implausible because every rectangle has a little bit hanging over. but it could be. So we'll explore that further. All right. So these are our conclusions regarding the right-hand sum. So our next job in part 3 is to do the same thing for a left-hand Riemann sum. All right. So here's what that left-hand Riemann sum is going to look like. If I can get to the page. All right. So now we're going to look at a left-hand sum. The left-hand sum underestimates an increasing function. So the true area is greater than the sum from I equals 1 to n of f of x by delta x. All right, and it's really strictly greater than as long as I have a finite number here, a finite number of n. Whether this area could be equal when n becomes infinite is sort of the open question of the moment that we're trying to resolve. But so now, see how much of this you can do 1 through 6. See how much you can set up now. But be careful because maybe check to make sure you're getting the sequence right first in the expression for x sub I because it's a little bit tricky. So see what you come up with for 1 through 3, and then I'll lay that all out in the next video.